Good evening, class. We are looking at the exam one review covering chapter 2, and we have several parts. So for the first part, we're going to cover 2.1, the tangent and velocity problems, 2.2, the limit of a function, 2.3, calculating limits using the limit laws. So the synopsis of what we cover is right here, and we're going to go over the first few sections. First and foremost, I want to remind everybody that when we take the exam, there is a pledge. So I'm going to quickly go over this before starting the exam. Here's the pledge. I pledge on my honor that I will neither give nor receive unauthorized assistance during this exam or any other exam for that matter. On authorized actions include but are not limited to the use of notes, text, graphic calculators, search engines, PowerPoints, or any other resources not explicitly allowed. I can't emphasize this enough. In other words, when you take the exam on your own. All right, let's therefore get started here. Limits of a function. Finding limits by numerical graphical method. Here's the definition, and we read it in this fashion. The limit of f of x as x approaches a equals n. The limit of f of x as x approaches a equals n. Now, let's take a look at these three cases. They look very similar. And we are interested in finding the limit of f of x as x approaches a. So we find a along the x-axis. And we're going to approach it from the left and right. As we approach it from the left, we are in this branch, and we are moving towards this point. As we move from the right, we are in this branch, and we are moving towards the same point. So from the bottom, we move this way along the y-axis. From the top, we move this way. And I hope you see that the limit of f of x as x approaches a is the y coordinate L. So the limit does exist. These two give this exactly same result. So what is the difference? The difference is f of a in this case is given as something else b, whereas here f of a equals n. In this case, f of a, we don't have it. There is a hole here. It's undefined. So part a, f of a equals n, which makes it continuous by definition of a continuity, which we will discuss later on, at x equals a. In part b, f of a equals b, but it's not equal to the limit. In part C, f of a is not even given, so it's not defined. But in each case, regardless of what happens at a, the limit of f of x as x approaches a exists, and it's equal to n. Horizontal asymptotes have a specific definition in calculus. If the limit of f of x as x approaches negative or positive infinity is L, then the line y equals L represents the horizontal asymptote. If the limit of f of x as x approaches a, this is a from the left, not a negative, okay? A from the left. And this is a from the right. If any of those, the result is negative or positive infinity, it gives rise to the equation of a VA, short vertical asymptote, x equals a. That's the definition. One-sided limits. A function has a limit at a if one-sided limits are identical. In other words, if you want to read this, limit of f of x as x approaches a from the left equals n, and limit of f of x as x approaches a from the right equals L, then the limit of f of x as x approaches a equals L. And if this limit is equal to f of a, then we say the function is continuous at x equals a. This is the definition of a continuity. So that's the synopsis of what's happening in this section. Okay. We want to find limits by numerical and graphical method and also algebraic or analytical method. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. F of x equals x minus 1 over x squared minus 1 is not even defined when x equals 1. Does it matter? The answer is no. Why not? Because we are not interested at f of 1, but rather we want to take the limit as we approach 1. And that's why we want to, if we want to go with the numerical method, we go from the left and right. So let's evaluate f of x equals x minus 1 over x squared minus 1 for values of x that approach 1 but not equal to 1. So what do? We make up a couple of tables. The tables give values of f of x for x less than 1 and x larger than 1. For x less than 1, for example, 0.5, 0.6, 7, 8, 9. But even 0.9 is way too far, so 0.99, and you keep on adding nines. Okay? So again, even 0.9 is way too far. Okay? And we put it into this function, f of x, and we do it with so many decimals. And even if they don't mention that, when you do a numerical analysis, you put a lot of decimals. Also, we're going to look at the same thing from the right side of 1. For example, 1.5, 1.4, 1.3, 1.3, 1.2, 1.1. Even 1.1 is too far. So 1.01 and so on. As we add more zeros between the decimal and 1, it gets closer and closer to 1. We put it in there, we evaluate it. This is what we get. Take a look at the last row because this is the closest number to 1 from the left, this one from the right. And according to this, when you look at the result, it should be that the table suggests the limit of x minus 1 over x squared minus 1 as x approaches 1 must be 1/2 or 0.5. So that's the numerical analysis. And by the way, you should only do that if they ask you. Now, if you want to graph this, you come closer and closer to 1. From the left, you're in this branch. From the right, you're in this branch. In both cases, you're moving towards this hole, which has an answer 0.5, the y-coordinate 0.5 or 1/2. Now, bear in mind that I'm going to remind you. When you are dealing with a rational expression where the top and the bottom have a common factor, where the common factor happens, it's the location of a hole. It's not a vertical asymptote, as you may recall from previous courses. So having said that, everything is fine. Let's look at it from an analytical point of view, algebraic view. That is more important than any other method, everybody. So having said that, how do we deal with that? If you plug in, you get 0 over 0, by the way, which we will discuss that later on. It's an indeterminate form. So we are going to factor. The top is fine. The bottom needs to be factored. And I hope you recognize that as x squared minus 1 squared or a squared minus b squared is a minus b times a plus b. And we're going to replace the bottom with x minus 1, x plus 1. So we can drop the common factor of x minus 1. And now you plug in. And I want to remind you this function is the same as this function. Okay, it's the same as this function, except this one has no hole, this one has a hole. Okay. In any event, now if you plug in, you get 1/2, which is exactly what we got with the numerical method as well as the graph. Either one should result in the same answer they do. Limit laws. Let f of x and g of x be defined for all x over some open interval containing a. Assume that L and M are real numbers such that limit of f of x as x approaches a equals L and limit of g of x as x approaches a equals M. Let C be a constant, some number. Then each of the following statements holds. Some law for limits. They are very straightforward. Limit of f of x plus g of x as x approaches a is limit of f of x as x approaches a plus limit of g of x as x approaches a, or simply L plus M. Meaning, the limit of the sum is the sum of the limits. Difference law for limits. The limit of the difference is the difference of limits, L minus M. Constant multiple law. If you are finding the limit of c times f of x, you can take the c out, c times L. In other words, the limit of a constant times f of x as x approaches a is the same as multiplication of a constant by the limit of f of x as x approaches a. The limit, this is called the product. The limit of the product is the product of the limits, L times M. Quotient law. The limit of a quotient is quotient of the limits L over M. Of course, as always, the denominator, in this case, M, cannot be 0. And we have the power law, and we have the root law. Those are very straightforward. One thing I want to add. When it comes to the root law, the limit of the nth root of f of x as x approaches is the nth root of limit of f of x as x approaches a is the nth root of L for all L if n is odd. But if for L being larger than or equal to 0 if n is even. So I'm reminding you, when the index is odd, there is no restriction. But if it's even, it's a different story. Just to tell you, to make sure everybody understands what we are trying to explain here. If you're looking at cube root of 8, you get 2. If you're looking at cube root of minus 8, you get negative 2. Not a big deal. If you're looking at square root of 4 is 2. But if you're looking at square root of minus 4, this is not a real number. This is 2i, where I, by definition, is square root of negative 1. That's why when n is even, we want to be careful. Okay? Okay. K is a constant. The limit of k as x approaches a equals k. If you happen to have a constant, it is independent of x, the variable. So as the variable x approaches any number, makes no difference, k remains unchanged. Direct substitution property. A continuous function at a has the following limit value, limit of f of x as x approaches a equals f of x. In short, you just plug in and you observe. Functions with a direct substitution property are called continuous at a. And finally, for this page, we have the squeeze theorem, also known this as the sandwich theorem. If f of x is less than or equal to g of x, less than or equal to h of x. In other words, g is some function between f and h. When x is near a, x possibly at a, and limit of f of x as x approaches a, the first function, and limit of h of x as x approaches a, the last one, equals L, the one in between, the limit of g of x as x approaches a, must have the same limit, namely L. This is known as the squeeze theorem. All right, let's look at some warm-up examples. Use the limit properties to find this. Well, Let's cut it into 1, 2, 3 limits. So limit of x squared as x approaches 4, plus limit of negative 3x as x approaches 4, plus limit of 7 as x approaches 4. That's using the limit laws. This one is the limit of x as x approaches 4 to the second power. This one, negative 3 comes. So now this one, I can replace it with 4. This one, I can replace it with 4. This constant is just 7. This is 16 minus 12 plus 7. It's equal to 11. Or simply plug in. If I plug in 4, I get the same answer, and that's fine. You can use that method. And basically what happens is that if the function is continuous at that point, it gives you an answer immediately, or it might give you a different format known as indeterminate there. Then we have to work on it and use our algebraic techniques to fix the problem. Given the graph of a function g, state the value, if they exist, of the following. We are interested in finding the limit of g of x as x approaches 2. We are going to look at one-sided limits, reminding you again, the way you read this, limit of g of x as x approaches 2 from the left, limit of g of x as x approaches 2 from the right, and we are interested in this one. So we are going to locate the 2 along the x-axis. And we're going to approach it from the left. As we approach it from the left, we are in this branch, moving towards this hole, which has a y coordinate 3. The limit of g of x as x approaches 2 from the right. So we're going to approach 2 from the right. That means we move this way. So we are in this branch. We are moving towards this hole, and it has a y coordinate 1. Are the two equal? No, the limit of g of x as x approaches 2, d and e does not exist. We are interested in finding the limit of g of x as x approaches 5. And again, we are going to look at the one-sided limits, limit of g of x as x approaches 5 from the left and right. So we locate the 5 along the x-axis, and we approach it from the left and right. It so happened in this case, as we approach 5 from the left, we are going this way. From the right, we are going that way, and both are taking us towards the hole. The hole has a y coordinate equals to 2. Therefore, because the left-sided and the right-sided limits are identical, the limit of g of x as x approaches 5 exists, and it's equal to 2. In the meantime, you have a solid point here, which makes g of 5 having this y coordinate about 1.4. And of course, it's not equal to 2. The limit exists. The functional value is not equal to that. It makes it, it's coming up. It makes it discontinuous at x equals 5. Okay. And there are different types of discontinuity. This is a removable discontinuity. As far as number 2 is concerned, we don't have a solid point, so g of 2 is not given, is undefined. This is, by the way, called a jump as image. All right, we are interested in finding the limit of f of x as x approaches 2. And again, we're going to look at one-sided limits. The limit of f of x as x approaches 2 from the left along the x-axis, locate the 2, approach it from the left. As we approach it from the left, that means we are over here. And we are moving towards this point, which has a y coordinate 3. Now, from the right side of 2, as we move this way, we are in this branch, moving towards this hole, which has a y coordinate 1. Are they equal? No. Therefore, the limit of f of x as x approaches 2 does not exist. What is f of 2? Well, you are looking for a solid point. This is a solid point. Y coordinate is 3, so f of 2 equals 3. Limit of f of x as x approaches 4. You locate the 4 along the x-axis. As we approach 4 from the left and right, from the left we are going this way, from the right we are going this way, and both of them are taking us towards this hole, having a y coordinate 4. So the limit of f of x as x approaches 4 does exist, and it's equal to 4. But what about f of 4? Look for a solid point. It's not given, so it's undefined. So what happens, the function is discontinuous at 4, but because the limit exists, it's fixable. We can fix it. It's a removable discontinuity. Whereas here it's a jump and there's nothing to do to fix the discontinuity. Reminding you of the definition of a VA, vertical asymptote, which is the limit of f of x as x approaches either a or a from the left or right is negative or positive infinity, x equals a, is a vertical asymptote. Starting with the first one, limit of r of x as x approaches 2. So you locate the 2 along the x-axis. As you approach it from the left or right, makes no difference. It's going down to negative infinity. The limit of r of x as x approaches 5. As you approach 5 from the left or right, makes no difference. It takes us up to positive infinity. Limit of r of x as x approaches negative 3 from the left. Here's negative 3. We are approaching it from the left. And from the left, it goes down to negative infinity. However, limit of r of x as x approaches negative 3 from the right, going this way takes us up to positive infinity. According to this definition, you look at this one, x equals 2. This one says x equals 5. This one says x equals minus 3. This says the same thing, x equals minus 3. Those are the vertical asymptotes. So we do have 3 of those. So how do we find limits? To find the limit, just plug in and observe. So when you plug in, what happens? Well, the limit of f of x as x approaches a is a number. You're done. If the limit is 0 over some number, it's equal to 0, and it's done. It's important to know 0 over some number means 0 over a number other than 0. If it's some number over 0, you have to figure out whether positive or negative infinity. We'll discuss that. We no longer say division by 0 is undefined. It tends to infinity or negative infinity. Which one and why, we'll discuss it as we come across examples. However, in calculus, most of the time we come up with indeterminate forms such as 0 over 0, infinity over infinity, infinity minus infinity, 0 to the power of infinity, and things of that nature. So there are different forms, which means you have to use some sort of a algebraic technique to fix it. So the way I'm going to define indeterminate forms is just more work. And you should have no problem handling it, okay? So the limit of the square root of x plus 4 minus 2 over x as x approaches 0. Here's an example. If I plug in 0, I get 4. Square root of 4 is 2 minus 2 is 0. And this is 0. So this is 0 over 0. And bear in mind, 0 over 0 means indeterminate, means more work, means use your algebraic technique to fix the problem. So the question is, what is the algebraic technique? The algebraic technique in this case is the conjugate. The way it works, the conjugate of a minus b is a plus b. The product is a squared minus b squared. Square root is a problem as far as you know how to fix the problem. So how do you get rid of that? You multiply by its conjugate. That means you write exactly the same thing. You change the negative to positive. But you are going to write that at top as well as the bottom. Why? Because this must be equal to 1, and it is. Okay? Now, when you get 0 over 0, it is the 0 in the denominator that we should get rid of. And this is the problem, which means you never distribute. You keep it as such. You just multiply these two, a squared, square root of x plus 4 quantity squared minus b squared. We get x plus 4 minus 4. 4 and negative 4 cancel each other. X cancels out the x, you get 1. And now if you plug in, you get 2 plus 2, 4 in the denominator. 1/4 is the final answer. One thing I want to add, because some students have seen limits. I want to look at these steps especially. If you don't write the limit, do all the intermediate steps, and then right here you write the limit is fine. If you don't write the limit here, you can't replace the x with 0. In other words, this expression is itself, but when you say limit as x approaches 0, it gives you a right to change it to 0. Now, we are interested in the limit of x plus 2 over x plus 3. One of them x approaching negative 3 from the right, one of them from the left. Now, what I want you to notice, if you never mind the left and right, say negative 3, the top is negative 1, the bottom is 0 in both cases. But it is extremely important when you have a number at top and 0 at the bottom, you have to know if the 0 is coming from the left and right. And here's the reason. If you have a positive number, everybody, let's make it up. For example, 5. The left side and the right side, for example, 4.9 from the left, 5.1 from the right, they are both positive. If you happen to have a negative number, negative 5, the left side is negative 5.1, the right side is negative 4.9. Both are negative. However, 0 is the only number. The left side is negative, the right side is positive. That's why you need to know. So in both cases, the numerator is close to negative 1, everybody. In other words, this one, negative 3 from the right, it's really negative 1 from the right, like negative 0.99. This one is negative 1 from the left. It's not important. It's very close to negative 1. But what about 0? Here's how you handle it. You say, okay, I need to know what happens to the bottom. So negative 3 from the right, you can even choose negative 2. But let's go closer. For example, negative 2.9 plus 3 is positive 0.1. So 0 from the right. But here, negative 3 from the left, you can even go with negative 4. But negative 3.1 plus 3, it's negative 0.1. So it's negative 1 over 0 from the left. So what is the difference? Both of them are infinity. However, negative over positive is negative infinity. Negative over negative is positive infinity. That's why when you have a zero in the denominator and a number in the numerator, you have to know the denominator. The zero is from the left or right. And one easy way, pick a number close by and check it out. All right, so let's plug in everybody. If you plug in 4, we want the limit as x approaches 4. So plug in, we get 0 over 0. 0 over 0 is indeterminate. That means more work. That means you use your algebraic techniques. So what do? In the case of a rational expression, you do factoring. One thing I want to tell you, because x is approaching 4, and we have 0 in the denominator, that means the denominator should have a factor of x minus 4. If x approaches 10, that means we should have a factor of x minus 10. If x approaches minus 8, we should have a factor of x plus 8. So that will help you with factoring. Obviously, the top is x times x minus 4. The bottom, you want two numbers. The product is negative 4, and the sum is negative 3. And you can easily see the factored format. You have a factor of x minus 4, you drop it. And now if you plug in, you get 4 over 5 as the final answer. And that's the idea. All right, again, let me clean up the mess. Plug in 0. We end up with 0 over 0. I hope you see that. If you replace the h with 0, you get 0 over 0. Same situation as the previous page. A minus b times a plus b is a squared minus b squared. You need the conjugate of the numerator because it's a square root. So you put a plus 1 in between. But bear in mind, this must be equal to 1. That's why you multiply it by the top and the bottom. And of course, as I mentioned, a minus b, a plus b is a squared minus b squared. So the denominator remains as a product, and the numerator is square root of 1 plus h, quantity squared minus 1 squared. 1 and minus 1 cancel each other. H and h cancel each other. And now you plug in, and you get 1/2. So pretty straightforward, everybody. The limit of the square root of x minus 6 plus 3 over x squared minus 7x plus 12, you plug in. I hope you see if you plug in 6, this goes to 0. So the numerator is 3. This one is 6 squared, 36. Minus 7 times 6, 42. Minus 42 plus 12. And it just works out. 1/2. 3 over 6, 1/2. Big deal. It works out. Fine. That's why you check it out in this man. What about here? If you plug in, I hope you see that obviously the bottom is 0. 1/3 minus 1/3 is 0. So you have 0 over 0. Because you're dealing with a complex fraction, you use LCD, which is 3x. And because x is approaching 3, x minus 3 is a problem. You never distribute the bottom. But when you distribute, this one gives you x, this one gives you minus 3, and you drop the common factor of x minus 3. And if you plug in, you get 1 over 9. So the technique for a complex fraction is LCD. In other words, simplified into a simple fraction. The limit of 5 plus h to the power minus 1 minus 5 to the power minus 1 over h as h approaches 0. I hope you see that if you plug in, you get 0 over 0. So the technique is to rewrite it. You recognize 5 plus h to the power minus 1 as 1 over 5 plus h, 5 to the power negative 1 as 1 over 5. And we are back with the same situation as part B. You have a complex fraction. You multiply by LCD, which is 5 times 5 plus h. And bear in mind, you multiply and divide. Because again, this must be 1, this must be 1. And you don't do anything to the bottom because h is approaching 0 and you want to get rid of it. So the bottom is h times 5 plus h. What is the numerator? If you multiply this one by this one, 5 plus h cancel each other, you get 1 times 5. If you multiply these two, 5 cancels out, you get negative 1 times 5 plus h. And as I mentioned, the bottom, don't do anything, just write it. So we just write the bottom. So the numerator becomes 5 and distributed. Minus 5 minus h, and the bottom we are not doing anything. We notice these two cancel each other. We notice this goes away and this is minus 1. And now if I replace it with 0, the bottom is 5 times 5. So negative 1 over 25 is the final answer, everybody. So it's pretty simple. The technique is LCD. And so we can handle that. We want to find the limit of f of x plus 5 times g of x as x approaches negative 2. And this is the graph we are going to follow. Having said that, we're going to cut this into 2 pieces. And so we're going to look at this piece, and then we're going to look at this piece. So as far as the red piece is concerned, we locate the negative 2 along the x-axis, and we approach it from the left and right. From the left, we are coming this way. From the right, we are coming that way. Both of them takes us towards this hole, having a y-coordinate 1. For g of x, that means the blue function, as we approach it from the left and right, puts us here, and this one has the y-coordinate negative 1. So we have 1 plus 5 times negative 1. Gives us negative 4, we are done. What about the limit of f of x times g of x as x approaches 1? We do the same thing. We cut it into 2 pieces according to the limit law, and we look at each piece, starting with the limit of f of x as x approaches 1. So along the x-axis, we locate 1. As we come across the left side of 1, takes us here, okay, for the red one here and here, which is the same y coordinate, namely 2. But for g of x, from the left, we go right here, and this one has a y coordinate -2. And from the right, we are moving towards this hole, which has a y coordinate -1. So the limit of g of x as x approaches 1 doesn't exist because the one-sided limits are different. Therefore, we say the limit of the product doesn't exist. By the way, if you have any type of an operation, okay, product, sum, you name it, and one of the limits, one of them doesn't exist, the other one, the sum, the difference, the product doesn't exist either. And you're done with that. The second method is to look at, when we go back to this one, look at the limit as x approaches 1 from the left and right. So from the left, then you want this one from the left, and this one from the left and right is the same, 2. You want this one from the left. From the left is -2, so the product of these two is -4. And then you want the limit of f of x and times g of x as x approaches 1 from the right. Again, this one from the left and right makes no difference, is 2, but this one from the right is -1. The product of these two is -2. Clearly, the two are not different, are not the same. The limit doesn't exist. Again, that is another approach. What is f of -2? So if you look at the red function, here's -2, and that has the y coordinate 2. G of 1, so look at 1, okay, at 1 for the blue function, the solid point is here, and the y coordinate is -2, just in case. The limit of f of x over g of x as x approaches 2. Well, it doesn't exist. Does not exist. Why is that? The g of x, the blue one, as x approaches 2, has the limit of 0. That's the problem. So the denominator, namely g of x, approaches 0, while the numerator approaches a non-zero number. So that's the reason. If g of x is between 2x and x to the power of 4 minus x squared plus 2, we, for all x, evaluate limit of g of x as x approaches 1. And I'm reminding you of the squeeze theorem, which indicates if you want to find the limit of a function in between, look at each piece and see what happens. So let's start with the left side. The limit of 2x as x approaches 1 is obviously 2. And the right piece, the limit of x to the power of 4 minus x squared plus 2 as x approaches 1. It's 1 to the power of 4 minus 1 squared plus 2. And I hope you know that this is 1, this is -1, cancel each other, we get 2. So this is +1, this makes it negative, don't mix them up. Therefore, because the two are identical, the limit of g of x as x approaches 1 must be 2 by the squeeze theorem. You must mention the squeeze theorem, everybody. Pretty straightforward, everybody. Prove that the limit of the square root of x times 1 plus sine squared 2 power x equals 0 as x approaches 0 from the right. So how do we approach that? And I want to go over that for everybody. The methodology, when you come across a case that involves sine and cosine and so forth, the sinusoidal functions first of all, we know they have a limit when it comes to their value is between -1 and 1. So because sine of alpha, beta, gamma, whatever, is always between -1 and 1, then this sine, 2 pi over x, doesn't matter, whatever it is always between -1 and 1. But this is not sine, this is sine squared. So we're going to square all sides. And I want to make a point that this is 1, this is sine squared. -1, if you square it, is also 1, but it's between 0. I want to emphasize this so everybody understands how that thing works. Okay? Because -1, between -1 and 1, we also have 0. So 0 is between the two numbers. From 0 to 1, when you square it, it's 0 to 1. And from -1 to 0, if you square it, this is 0 and this is +1 also. So it's between 0 and 1. So I want you to be careful with that. If this was, let's say, 2, this was 5, you would say 4 and 25. That makes sense, but that's not the case here. Now, the idea is to make it look like this. And to make it look like this, what is missing? Number 1. Therefore, add 1 to all sides. So to do so, this becomes 1, this becomes what we want, and this becomes 2. So far, so good. What else do we want? Well, we want square root of x. So let's multiply all sides by square root of x. And remember, when you multiply or divide by a negative number, it flips over. But x is approaching 0 from the right, so you do know it's positive, so nothing changes. And now this looks exactly like this. So you are going to go with the squeeze theorem, and you will look at the left side and the right side. As you can see, the limit of square root of x as x approaches 0 from the right, and the limit of 2 square root of x as x approaches 0 from the right is the same thing, namely 0. If that is the case, therefore, the limit of the given square root of x, brackets 1 plus sine squared 2 pi over x as x approaches 0 from the right must be 0 by the squeeze theorem. Find the limit of 2x plus 12 over absolute value of x plus 6 as x approaches -6. Let's evaluate this, and to do so, I'm going to remind everybody. Okay, so I want to look at one-sided limits. As you know, the absolute value of x by definition is distance from 0. That's equal to x if x is larger than or equal to 0, and minus x if x is less than 0. So the absolute value of x plus 6 is x plus 6 if x is larger than or equal to -6. In other words, set this equal to 0. And it's the negate, you negate that minus of the parenthesis x plus 6 if x is less than -6. So as we approach -6 from the left, okay, first of all, the top, you factor the 2, you get 2 times x plus 6. The bottom, you drop the absolute value. From the left, according to this, you put a negative in front of a parenthesis. X plus 6 cancel out. You get 2 over -1, or simply -2. And the limit of -2 is -2. If we go with the right side, in other words, taking the limit of 2x plus 12 over absolute value of x plus 6 as x approaches -6 from the right, again, the top, you take the 2 out. The bottom, you just drop the absolute value. According to this, becomes x plus 6. They cancel each other, and you get 2. So, because the two are different, one-sided limits are different, the limit of the function 2x plus 2 over absolute value of x plus 6 as x approaches minus 6, D and E does not exist. And why? I just said it, they are different. Second methodology would be to simplify the expression in the first place. 2x plus 12 over the absolute value of x plus 6 is 2 if x is larger than or equal to minus 6. Take a look at this. And negative 2 is if x is less than minus 6. And then you look at the limits that way. Either way, the limit doesn't exist as x approaches negative 6.